Today we're going to be doing lesson 7-5, dilations. Our target, I can identify and create dilations of plane figures. And just to unpack that a little bit, when you see the word plane, we are not referring to boring or simple, but instead we're referring to two-dimensional figures. So when we get to our geometry unit in a little while, we'll learn a lot more about plane figures. For now, just know that we're talking about two-dimensional shapes, and specifically dilations, as you can see in the definition, is a transformation that changes the size but not the shape of a figure. A dilation can reduce or enlarge a figure. As you could probably guess, those words, if something is reducing, it is getting smaller. Let's write that down. And if something is enlarging, it is getting bigger. And you've probably heard the word dilate before. Something that we often think about with dilation is our pupils. Pupils dilate. Of course, that's the center of your eye, and that dilates depending on how much light it's trying to let in, so it can be changed depending on the darkness inside of a room or outside. Also, something can affect your pupil, like if you are scared or concerned or something along those lines, your pupil can change sizes. But think about the human pupil never changes shape, right? It's always circular. It just gets larger or smaller as it dilates. So today we're going to be talking about figures that dilate. So this little picture of Snoopy is a good example. The picture itself is the same exact shape, but it has changed size. And we can dilate images whenever we insert them into a document as well to make them larger or smaller. We've talked about how when we want that image to be proportional to the original, we want to pull the sizing from the corner so that it's not distorted. And so when we are doing that, what we're really doing is we're changing it by the same scale factor. So a scale factor is going to describe how much a figure is enlarged or reduced, and it's expressed as a decimal, percent, or a fraction. Now, when you see the word factor, we are always thinking multiply. So this scale factor is a number that is going to be multiplied by your dimensions or by your coordinates. We'll see both of those today. Now, when we have a scale factor between 0 and 1, that's when it's going to reduce. So it's going to get smaller. And that makes a lot of sense because we just learned about multiplying by fractions or decimals between 0 and 1. And we know that that makes the value smaller. And a scale factor greater than 1 is going to enlarge it. And that also makes sense because if we multiply by a number bigger than 1, it's obviously going to be bigger. So those are fairly logical. Some of you are probably sitting here and saying, well, what if it is exactly 1? And as you could probably imagine, it's not going to change size at all. So then it wouldn't really be a dilation if the size has been maintained. We are expecting it to either be larger or smaller than the original. Okay, so next we're going to look at how to find the center of dilation, and also a way to prove if something has been dilated or not. So let's take a look here. It says to locate the center of dilation, point O. So one very interesting feature, if we are looking at a dilation, is it's going to have a center of dilation found by connecting all of the corresponding vertices. So we talked about this a little bit in the Are You Ready at the beginning of chapter 7, but corresponding means they're in the same spot within the shape. And conveniently, they're going to be lettered the same. So we have A, and then we have this A with an apostrophe, just so we know for future that is pronounced A prime. So put in quotations, A prime. Anytime we have dilated a figure, We want to show the corresponding pieces by using the same letter, but we now use the apostrophe to show that it is actually a new figure. But if we connect those corresponding pieces, we should be able to find our center of dilation. So I'm going to do my best to draw a straight line. If you have a ruler, you can certainly use that as well. That's helpful sometimes. But I'm going to go ahead and connect A prime to A, and then B prime to B, and finally C prime to C. And when I do that, I'm going to get a single point where all three of those lines intersect. This is known as the center of dilation. If I do not find that they intersect, that actually proves that it's not a dilation at all if there's no center. Let's do the same thing for these rectangles over here. So we'll go ahead and connect the corresponding pieces. So A to A prime, B to B prime, C to C prime, and finally D to D prime. And we can see that our center of dilation is actually going to be all the way out here. Now, a feature of these figures that are dilations, as I mentioned above, is that their side lengths are proportional. So if they're proportional, we know that they're equivalent ratios. So when you see them drawn on a graph here, and we are looking for whether or not it's a dilation or not, one thing to take a look at is, are the side lengths proportional to one another? So if I look at this smaller rectangle here, I see it has a base of 3 and a height of 2, and I'm just counting the blocks. For my larger rectangle, it has a base of 1, 2, 3, 4, 5, 6, and a height of 4. So when I think about that, and I want to be consistent in my setup, but if I set up the longer side versus the shorter side, in my first rectangle it was 3 over 2, and in my second rectangle it was 6 over 4. And I can find that those are the same by finding a common denominator or simplifying both, however you want to do it, and we end up seeing that they are in fact equivalent. So that is one thing we're looking for. Also, we can see that they are the same shape, so that helps us to know as well that these are considered a dilation. If we wanted to then, we could find the center of dilation again by connecting these. That was not good. Here, let's try that again. And we can see that our center of dilation is right around that point right there. Okay, and the next one, if I look at the side lengths, and in a triangle I can just look at base and height. In the bottom triangle we have a base of 1, 2, 3, 4, 5, 6, and a height of 4. And in the smaller triangle we have a base of 5 and a height of 4. Okay, now if I set those two up, and again I do the longer side over the shorter side, then I had 6 over 4, and I had 5 over 4. Now, a lot of you could probably see already there's no way those could be equal because they have the same base or denominator, but a different numerator. And so this is not a dilation. And just to kind of show when we go to connect the vertices, what you're going to see is going to happen is these two are never going to meet up because they have actually formed a set of parallel lines. So there actually will never be a way to find a center of dilation because it isn't a dilation to begin with. Okay? All right, on the next page, in example 2, it says to dilate each figure by the given scale with the origin as the center of dilation. And that's generally what we will see, the origin as the center, not always, but most of the time. And it says, what are the coordinates of the image? So this is going to be very important on tonight's homework. Your homework is not very long, but when it asks for the coordinates, you need to not only dilate the figure and graph it, but you also need to list what they are. So to start, we're going to actually list what the 4 original coordinates are, and we'll just do that down below. So starting with point A, remember from the origin, I'll go to the left first, and A is at -6, and then up 1, 2, 3, 4. Point B is on the y-axis, so the x is 0 and the y is 4. Point C is at the origin, so 0, 0. And point D is on the x-axis. We go to the left 6, but then don't go up or down, so the y is 0. Okay, now you'll notice that this scale factor here is 1/2. So before I even begin, I know that this is going to be a reduction. It's going to reduce because I have a scale factor between 0 and 1, so it's going to get smaller. But how I'm going to do this, because we can, again, we said factor means multiply, we are going to take each of these coordinates and multiply them by 1/2. So you can actually show that right here in the point if you would like. And then we're going to draw a little arrow and show that the new coordinate, which remember we're going to call A prime, would now be -3, +2. B prime, I'm going to do the same thing. So I multiply the original coordinates of B by 1/2. And I see that B prime is going to be 0, 2. 0, 0 multiplied by 1/2 is just going to stay 0, 0. So C prime is still at the origin. You'll see how that looks in a moment. And then D, when I multiply both coordinates by 1/2, I'm going to find that D prime is going to be -3, 0. So now we're going to actually go back up to the coordinate grid and we're going to plot each of our new points to see the dilation. So A prime is -3, 2. So from the origin, I'll go to the left 3, up 1, 2. And that is my A prime. B prime is at 0, 2. So I'm going to go to the, I'm not going to move to the right or left, but I'm going to stay on the axis and go up 2. My B prime goes right there. We said C prime stays at the origin, and D prime was at -3, 0. So now I'll connect my points, and I can see that I have my mini rectangle. It looks to be exactly the same shape as the original, but obviously it is smaller. So to complete this problem, just to recap, you'll list the original coordinates first. Then you'll use the scale factor multiplied by each of the original coordinates to get your new coordinates. Then once you get your new coordinates, you will plot them, and that is the dilated image. Okay, let's try one more. So here we just have a triangle with points A, B, and C, so let's list them here. So coordinate A is to the right 1, up 1, so it's 1, 1. Point B is to the right 3, up 1, so it's 3, 1. And point C is to the right 3, up 3, so it is 3, 3. And this one has a scale factor of 3. So I know that it will enlarge my figure. It's going to get 3 times bigger. So now to find what my new coordinates are, I'm going to start with A. I'm going to multiply each one by 3. So now A prime is 3, 3. B prime, when I multiply both B values by 3, will be 9, 3. And finally, C prime, when I multiply each one by 3, will be 9, 9. So now I'm going to go back up to my coordinate grid. 3, 3, I go to the right 3, up 3, and it actually coincides with the original point C. That's okay. That just means they share the same location. B is 9, 3, so from the origin I go to the right 9, up 1, 2, 3. And C prime is when I go to the right 9, up 9. So that's going to be all the way up here. Notice that every time I plot a point, I label it. That's very crucial because you're showing what the coordinate actually is, you're naming it. And it's also crucial that you use the primes because that's indicating that it's not the same point as the original. All right, let's go ahead and connect them. And so again, we see We have a same shape, but obviously it has gotten much larger. And now each of the sides is actually 3 times larger than it was. And the whole figure has been enlarged. Okay, last one. In example 3, it says to dilate the figure by a scale factor of 1.5 with A as the center of dilation. And then the hint is to measure the sides first. So I did that for you approximately. So I'll just show you. This is a question you're not going to see often, but I just want you to be aware that sometimes you might not even have the coordinate grid and you're still going to be asked to dilate a figure. I also want to point out from the start that because this was a scale factor of 1.5, it's going to enlarge. Because remember, anything bigger than 1 will enlarge the figure. Since it's a value larger than 1 that we're multiplying by. So I pre-measured these sides, and AD is approximately an inch. And AB is approximately 1.5 inches. So it's a little different how we're going to do this one. We know in a rectangle, the opposite sides are the same. So we know that if AB is 1.5, so is DC. So that's a little bit helpful. We know if AD is 1 inch, so is BC. So essentially what we're going to do is we're going to take the segment AD, which equals 1 inch, and multiply by our scale factor of 1.5. So now we know that our new height of the rectangle will actually be 1.5 inches. Now we'll do the same thing for our base, which was segment AB. So if AB was originally 1.5 inches, and now we multiply by our scale factor of 1.5, we will now get 2.25 inches. Now, to actually create the dilation, we are told that A is acting as the center of dilation. Now, that's kind of interesting. What that means, again, is that all of those corresponding lines connecting the new image to the original corresponding vertices is going to intersect at the point A. So really what that means is the segment is just going to be extended in a way. So if AD is now supposed to be 1.5, that just means we're going to extend it 1/2 of an inch to approximately right here, and that would be our new D prime. Likewise, if AB is going to extend to 2.25 inches, then it's going to extend about 3/4 of an inch this way. And again, we would do more exact measuring, but I'm just giving you the idea here to put B prime right there. And then that would mean that these two will meet up out here, and this point would be our C prime. And that's how we could have created the dilated figure. So that means that from A to A prime, of course, this was 2.25 inches. And from A to D prime, that is now 1.5 inches for the dilated figure. All right, thank you.